Okay, good morning, everyone. Okay, before we start, and I would like to talk a little bit about the quiz because some did well as usual, but some had some misunderstanding. So I will go through it one by one, and as I am going through it, please make sure to ask questions. I will only go through the problem where most of you had difficulties with. 1A, nobody has any problem with that. 1B, there were a little bit of issue with the radius. So I will remind you what 1E is about, 1B is about, and then what was the issue that some of you had. And please ask question as I am moving on. So the question is, I gave you a curve and I drew it for you. I put this as a 1 and this is a 3 in here. And the curve was y equal 1 over 1 plus x squared. That was my curve. And I gave you the axis of rotation to be the line x equal to 3. That was the axis of rotation. And I told you that I want you to use the shell method, so you guys knew exactly which approach to use. Okay. And the shell method means you have to take slices parallel to the axis of rotation. So it means in my mind, we're dividing the interval from 1 to 3 into pieces, and we are rotating every piece around the line x equal to 3. Every time I rotate one, I get a shell. So I'm kind of having a shell inside the shell inside the shell. That's how I'm approximating the volume. So I can take the first shell if you want. I rotate it. This gives me a shell. Then I rotate the one next to it, then next to it. And the idea is to find the volume of each one of them, which is tedious. So we take what I called in class a typical one. A typical one, it means you don't take x to be 1. You have to take just an arbitrarily x in here. So totally parallel, it means you take this little piece here, and this is the one you rotate. And I insisted you guys rotate because some of you are, I don't know, they give me right answers with the wrong picture. It doesn't work this way. Okay. All right, so this is a shell. Now characterize the shell is the radius, the height, the thickness, and the volume. All right. Where the difficulty came? The difficulty came with the radius. And what I think is the problem is the radius is from here to here. That's the radius. The problem is understanding of the xi. What the xi is the distance from 0 to here. This is my xi. In other words, some students are thinking of xi this way. Xi is within the region. It's not here.
You got it.
Question? Okay. If this is xi, so the radius is going to be the right value minus the left value. Otherwise, you're going to get a negative answer. So the xi, I think that was the misunderstanding. I'm trying to see it, is from 0 to the slice. That's what your xi is. The radius is from here to here, which is the right minus the... So that was the issue with problem number 1B. The rest was simple. Nobody had issue with that. question about 1B, please go ahead. Your exam is this week. I want this to be clear. All right. All right. Now, so that was the issue. Now, in problem number 2, also there were some issues, and I will try to clarify them the best I can. This is the question. I gave you a curve, and it was y equal e to the x. That was my curve. And this is ln of 3. And this is y equal e to the x. So a lot of you figured out this point correctly. If the x is the ln of 3, the y is e to the ln of 3, which is 3. So this was okay. And my rotation now is about this axis. And I told you to use the washer's method. So the washer's method means any student who did something like this is not doing it right. Even if their answer is wrong, is correct, I don't know how they did the wrong picture with the right answer. It doesn't make sense to me. So the way we do it is, again, we are cutting this into pieces, and we are rotating every piece. Every time I rotate it, I get a washer, another washer. So I'm filling the rotated, the solid with a bunch of washers. So I concentrate on one of them. This one right here, little piece. Little piece. And this is, you put here your xi. So xi for my mind is from here to here. Immediately, x is the variable. Immediately, x is the variable because you're dividing the interval on the x-axis. X is the variable. There is no y variable in this problem. Now, we rotate. For the washer, you need the outer, you need the inner, you need the height, which is not really a problem. It's always the delta x, delta y. It has to be the delta x here because I am on the y-x axis. And then the volume that I have also to make comments about. All right. What is the outer radius? That's the axis of rotation. So you're taking this little piece and you are rotating it. So your outer is from here up to here. That's your outer radius, which is obviously equal to 3. That's the center of rotation. That's the center of rotation. Now it's the inner that you struggled with. The inner is from where to where? From the axis of rotation to here. That's your inner. Please make sure all of you understand what I'm saying, or try at least. Now, what's the inner? That's 3 in here. Down here, that's xi. It means this point, which is on the graph of the function, that's e of xi. So the inner is going to be from here to here. Means it's the upper value minus the lower value. A lot of you wrote e to the xi. E to the xi is this is e to the xi. That's not what you want. You want from here to here, which is 3 minus e to the xi. So the outer is 3. You didn't have problems with that. You struggled with the inner, which is 3 minus the xi. Remember, e to the xi is from the x-axis till you hit the curve. That's e to the xi. This one is 3 minus e to the xi. And the volume. Let me write the volume clearly. Some of you also are not struggling, but forgot the formula. So the volume is pi times. It's the outer square minus the inner square. Some students are doing the following. Outer minus inner, and they are squaring this. This is absolutely false. That's not what we have. It's the outer square minus the inner square times the delta x. So the other mistake came up with the volume, and student kind of got it wrong. You don't take away the inner from the outer and you square the result. You take the outer square minus the inner square times the delta x. And now the total volume became the integral from 0 to ln of 3 of pi times The outer square is 9. The inner square is 3 minus x. And then you look up the solution, and I have how to integrate this. All right. The only remark is few of you did the following mistake. Antiderivative of e to the x is a half e to the 2x. Some of you did a mistake at this stage. Question before I address the last problem. Any questions? Please go over the remark I made and make sure you're making a little bit sense what you did wrong. That's the only way you learn. The last problem, and I agree, when I gave it to you, I had a stupid mistake, but I corrected it during the the lecture. I try not to do this mistake next time. So I had this type of curve, and this was the correct one, was y equal x minus 2, and this is y equal the square root of x. Okay, so this was the region. And I rotated it about the y-axis, and I told you do it the way you want. I did not put any condition on that. First, let me talk about the intersection. So intersection point. You can find the intersection in two ways. Either you set the y is equal, or you set the x is equal. So let us say you set the y equal. Means you set this equal to that. Some of you just stared at it. And you have to solve. The only way you can solve this is by squaring both sides. So this is x minus 2 squared. It means x equal x squared minus 4x plus 4. And then this is x squared minus 5x plus 4 equal to 0. Would you show me the steps of evaluating on number 2? Yes, I will do that. I will do that. But let me finish this. I will keep that in mind. All right. And so this equal to 0. So that's a 4, a 1, x minus 1, x minus 4. So that's going to give me x equal to 4, x equal 1. And what is the intersection? Okay, if I put 1, it's not going to work, because if I put 1 in here, I will have square root of 1. If I put 1 in here, I will have minus 1. So minus 1 has to go. How about 4? If I put 4 here, I get a 2. If I put 4 here, I get a 2. That's my intersection point. Okay? So we got the intersection. Now the approach. And this point here is 2. You can do it two ways, which is the easier and which is the harder one. So I would start by the easier one, and then we talk about the other one, which is not hard, but it's different. The washer. Washer, that's my axis of rotation. It means these are my pieces. That's the washer. Yi is the variable. Immediately, what is the variable? The washer, it means in my mind, I'm dividing this interval into pieces, and I'm rotating every one of those. So y is the variable crucial. Everything has to be in terms of y. All right. Everyone who did it washer got it immediately correct. The inner is from here to here. That's the inner. So this will give me x equal y squared. Outer. Again, from the axis of rotation till the farthest point from the axis of rotation. That's the outer. If I solve, I get x equal y plus 2. So the washer was not difficult. So the washer, the volume will be the integral from 0 to 2. I am on the y-axis. Pi times, again, it's the outer square minus the inner square, not outer minus inner square, and of the washer. Now, shell. So I will draw it again to talk about the shell. And this is for 2. Okay, so this is the shell. Remember, the shell, you have to take slices parallel to the axis of rotation. And that's what happened with the shell. If I take my slice right here, so this is my x here, and I rotate it, the height is from the x-axis all the way to the curve. However, if I take my slice right here, the height is between y equal root x and the line. So the formula for the height is actually changing across the region. So I need to split all the way up to here because the formula will have to change. So I'm going to call this D1 and this D2. So the volume is going to be the volume by rotating D1 plus volume by rotating D2. There is not one formula across the board. That's why graphing is important. And writing those slices is important. You can start watching them. Now, for the one rotating D1, it means I am from here to here. The radius is always xi, but the height is only the square root of x dx. That's D1. D2 is from 2 to 4. That's the D2. The x is the same because I'm still rotating this piece around the y-axis. So my x is going to be the same. But my height is a very different formula. So my height here is going to be root x minus, right here, y equal x minus 2. That's the height in this scenario. And now you have minus x minus 2 dx. Okay, so that's how we do it if you use the shell. Neither one of them is hard, but if you do the shell, you have to split. And the reason is we have two different regions. So you'll have your choice as long as you do it correctly. Okay. Okay, I'll finish with the questions that you guys ask, and then we'll move on. You asked me about evaluating this integral. Okay, I will do that. So this is number 2. Okay, and the evaluation is we have the integral from 0 to ln of 3 of pi times 9 minus 3 minus ex squared dx. Okay, is this your question? The one who asked me the question from the classroom. Is this what you want? Say yes or no. Classroom, is this your question? Yes, okay, great, equal. We have to distribute here. I don't know what else to do. I mean, there is nothing else we can do actually. So this will give me 9 plus e to the 2x minus 6 e to the x. You distribute correctly. So this would be equal to pi times integral from 0 to ln of 3 of 9 minus 9 cancel each other out, and I will have minus 6ex minus e to the 2x dx. Okay, and now you can do it one by one. I mean, if you look at this integral, the antiderivative of this piece, we know it. So it's going to be pi times. The antiderivative of this is 6ex, not hard. Then you have the antiderivative of e to the 2x. Now, eventually, you're going to memorize what's the antiderivative of something that look like this because they come up a lot. And then I said last time is for this one, you can totally, this piece only. This one you can isolate, and you can say integral of e to the 2x dx. You need to find it by itself. You don't have to combine. U is 2x, so du is 2 dx. So this will become a half e to the u du. It means a half eu. It means a half e to the 2x. So the antiderivative of this piece is 1/2 e to the 2x. You don't have to do them combined, because if you just look at it, this is easy and this is a relatively easy one. So you can split the integral. We evaluate this between 0 and ln of 3. And now that's the evaluation piece. 6 e to the ln of 3 minus 1/2 e to the ln of 3 minus 6 e to the 0 minus 1/2, which is 1. So finally, I will get pi times e to the ln of 3. We know that e to anything is 3. So you will have 18 minus 1/2 e to the 2 ln of 3. You can do it several different approach. One way you can say that using the property of log is e to the ln of 3 squared. You can bring this. It means e to the ln of 9 equal to 9. Or you can say e to the 2 ln of 3 using the power of property of exponent is 3 squared, which is 9. And then you will have minus 1/2 times 9 minus 6 minus 1/2. At this stage, it's very, very simple. And if my memory is right, you should get 8 pi. Okay. Any other questions before I proceed? So please make sure you understand your mistake. That's the most important part of learning. You should know how to do it. If you don't, and that's the goal of the quizzes, just to let you know, okay, what did you do wrong? What did you do wrong? And please label, draw, label. That's how you understand this material. Okay. Any questions before I move on? Okay, this week will be relatively easier because you will not have to come up with your formulas. Most of them, the time I will be giving you, it's a simple formula. So this week will be relatively easy. So section 6.5, arc length. Okay. First, let me motivate a little bit the idea. See what we are talking about. You don't have to write for a little bit. You're going to be encountering a lot of curves, and you guys will be talking a lot about curves. So we call this a curve. And a curve is nothing more than what I'm drawing in front of you. And in math, most of the curves that you will encounter are going to be the graph of functions. So you graph a function, you get something like that, and we're going to call this a curve. So the curve is the graph of a function. And the question is, suppose you have a function, so you know every point here. So if you have the function, it means every point on the graph, you know it. The question is, what's the length of the curve? What does it mean, the length of the curve? What's the length? You can think of lengths two ways. One way you can think about is that if you take the curve and basically you stretch it and you measure it, how much it measures. That's the length. Aiden, I didn't understand what you wrote. Okay. Now, another way you can think of the length is, imagine you have a bug or something moving along the curve, starting from here and moving along the curve. What's the distance this object traveled? The distance it traveled is exactly the length of the curve. So you can think of length of a curve, either take the curve, stretch it and measure it, or an object moving along the curve, what's the distance they travel? So that's the length of the curve. And the question is, of course, if we know the function, it means I know every point on it, how to find the length. Anybody come up with any idea? How do you think we're going to approach this problem? I know it's Monday, but you guys can still think. It's not an easy problem. What's the easiest thing we can find the length of? What's the easiest thing we can find the length of. What type of curve? If I give it to you, you can find the length of it. Are you guys with me? Circle. It's actually very hard, the circle. I want something very easy. Circle is very hard. Straight line. I give you a straight line, and you're gonna find the formula, and I give you every information. I tell you what this point is, what this point is. I tell you find the length from here to here. It's gonna be very easy. So how do you think we're gonna find the length of any curve? Remember how we found the area. We approximated it by area of rectangle that we know. Find volume, we approximate it by cylinders or shell. We're gonna definitely have it, as Jana said, sum of lines. So to find this, the way we're gonna approach it is, we're gonna cut this into pieces. That's the only way we can do. And do the following. Sum of lines. And I'm gonna take this line, find its length. This, and then find the lengths of every line. And the more subdivisions, the better approximation of the lengths we have. So the idea would be we're going to cut it into pieces. We're going to find the length of this line plus this, plus this, plus this, every one of them, get the Riemann sum, and then find the form. So that's exactly what we are going to be doing today. So step number one is, let us remember what's the length of a line segment. And then from here, we are going to move back to here. All right, so that's what we will be doing today. Okay, I get started. So first, distance between 2 points. So now I'm going to start the approach. So first, distance between 2 points, or the length of a line segment. Okay, so let's say I have 2 points. A, let's call it x1, y1, and B, x2, y2. And I have this point right here. And the question is, what's the length of the line segment, or the distance between two of them? So length of line segment AB, which is usually we denote it by like the absolute value sign. So we denote by this is equal to. Okay, what's the distance between 2 points? I mean, all of you should know the formula by now because it's Pythagorean theorem. We draw this rectangle, sorry, it's this triangle. From here to here, that's the change in y. From here to here, that's the change in x. We use Pythagorean theorem and we get the square root of the change of x squared plus the change in y squared. Okay, that's Pythagorean. All right, so that's very easy. That's why we always approximate. Whatever the problem become hard, we're approximating by stuff we know how to do. Line segment are the easiest type of curve that you work with. But of course, calculus is not about line segment. Calculus is about things that actually curve. That's really always my problem. So now, part 2 is the setup. So that's the setup. Let's see. Usually we use the letter C for a curve. Let's see. Be the curve. What type of curve? The curve which is the graph. Which is the graph of a function, which is the graph of f of x for x between a and b. The question is, find the length or the arc length. Arc length, it means length of an arc. And a curve is just like, you can think of it as an arc. So find the length or the arc length of the curve C. And our approach will be, as I said at the beginning, so we're going to take the interval AB and divide it into n equal subinterval. And approximate the length with sum of the length of the line that will explain, sum of length of lines. As follows. Okay, so that's really the idea. So I'm going to draw the picture again, I'll show you the line, find the length of each one of them, and then derive the formula. So I go back to my starting point. That's going to be the curve. So this is my point A. That's it. So this is my point A, and this is B. Now, how we are going to get those lines? We will get those lines as follows. We're going to divide this into little pieces, x1, x2, xi minus 1, no, sorry, xi plus 1. So we're going to divide this into pieces, and this is my xn. And the line are as follows. This is the point A. So my first line is from here to here. That's the first line. I need to find its length. My second line is, I take this point right here. It means this is x2, f of x2. And I take this line from here to here. And I want to find its length. And then I keep going. x3. So that's really the picture. And I want to find the length of this plus this plus this. So as we did before, instead of working with every one of them separately, I say, okay, let me take an arbitrary one. That's what we always call. And find the length of one like this one. Okay, so instead of doing the same thing several times, I focus on one of them and I try to find its length. So I'm going to call this point Pi. And this is, I will call it Pi plus 1. So this is the point P0, P1, and so on. So I want to find the length of Pi plus 1. Before we do that, what are the coordinates of the point Pi? This is xi. It means this is f of xi. Pi plus 1, this is xi plus 1, f of xi plus 1. And my whole concentration now is, what is the length of Pi plus 1? If I can find this, then I can add them. All right. Based on the distance between 2 points, this is equal to the change in y plus the change in x. Okay. All right. Now, because it's tedious to write xi plus 1 minus xi, let us see the picture right here. Xi plus 1 minus xi is nothing more than what we call the delta x. That's really a delta x. So instead of writing this, I'm going to write delta x. And from here to here, I'm going to call the delta y. Now, the delta y changes between the point. So between this and this, that's the delta y. From here to here, that's the delta y. So every line segment has a different delta y, but the delta x, we are really keeping it the same. So, but just we can simplify a little bit the writing. So it's going to be equal to the square root of the delta x square plus the delta y square. Just look at the picture so I don't have to write this. Now I'm going to do something a little bit not magical, but to make the formula clear. I'm going to factor out the delta x, and then I will be almost done. So I'm going to put delta x squared here, and look what I get. If I factor out the delta x squared, I will get 1 from here. If I factor out the delta x, I will have delta y squared over the delta x squared. So I factor it out, so I have a delta x in the problem. So finally, this will give me the following. Since this delta x is square, I'm going to put it up here. And this will give me delta y over delta x, the whole thing squared. Okay, I'm going to stop, not stop, let you write. And now I'm going to ask you this question. I want answer. I will not give you the answer. I want to take back to this picture, ask you the following question. Delta y over delta x. If delta x is small, what does this remind you of? If you take the delta y over delta x, this reminds you of what? I want answers. Slope, very good. Slope of what? I will keep pushing you till you tell me what the answer is going to be. The slope of what, Josh? The tangent line. Do you agree with Caitlin? Is it the slope of the tangent line? When delta x is small, delta y over delta x is basically the slope of the tangent line. Absolutely correct. So this is almost equal to the slope of tangent line at xi f of xi. Beautiful. What did we call the slope of the tangent line? Back to you. What name did we call the slope of the tangent line? Derivative. This is exactly the derivative at xi. Okay, so let us recall what we did. We played a game and we brought the delta y over delta x. Now, delta y over delta x, as your classmate said, when delta x is small, is almost the slope of the tangent line. What's the slope of the tangent line is nothing more than the derivative at xi. And this becomes the magical formula here. So this is going to be equal to, almost equal, because we're approximating, 1 plus the derivative at xi squared times delta x, which means that this little line segment, its length is the square root of 1 plus f prime of xi squared times the delta x. That's the length of this little line segment. And now we are ready to come up with the formula. So the arc length, the length of the curve, is going to be approximated by the sum of the length of every one of them. It means by the sum of those. That's what we are approximating bitwise. It means it's the sum of the following, of the square root of 1 plus the derivative square times delta x. So the length of the curve is going to be the sum of those stuff. That's our typical Riemann sum. And so by the definition of the Riemann sum, we will have the following. So we're going to have the following. The length of the curve C given by the graph y equal f of x for x between A and B is, sometimes we use the letter L for length, that's fairly common, is the integral from A to B of the square root 1 plus the derivative of f squared dx. And that will be the arc length. How it came up, the formula is very, I like the way the formula has been derived. It explained to you really where somehow we're getting all those weird formulas from. So that's my curve C, and that's the length of this curve. I will do two examples immediately. Now for this problem, of course, I'm not expecting you to derive the formula. I'm expecting you to be able to use the formula in like volume and area. Okay, so example. Now, those integrals are very hard usually to evaluate. They involve a square root of a term. They are very, very hard to evaluate. But the problem that you guys will be given, which is not a lot because the difficulty of integrating those, you should be able to handle them. So let me take a simple example. So let f of x equal x to the power 3 half. Okay, for find the length of the curve given by f, by the graph of f for x between 1 and 4. Okay. So the graph here usually not, you don't really need it a lot because you have to use the formula. X to the power 3 half is usually go like that. It's more like a parabola. This is 1 and this is 4. So I'm not interested in this piece. And the question is, what's the length of the curve from here to here? So imagine you have an ant or a robot or something moving along the curve. And you want to find out, okay, what's the distance traveled? That's really what's the length of the curve. All right, so we have to use the formula. So L is integral from 1 to 4 of the square root of 1 plus the derivative squared dx. Okay, so the first step, we have to find the derivative. There is no way out. So my function is x to the power 3 halves. So f prime is 3 half x to the power 3 half minus 1, which is a half. So the arc length is integral from 1 to 4 of the square root of 1 plus the derivative squared dx. So finally, this is equal, not finally, sorry, this is the integral from 1 to 4 of the square root of 1 plus 3 half x to the power a half square. It means you multiply this by itself. 3 half plus 3 half is 9 over 4. X to the half square is x. So now I have to integrate this function. So quickly, how we do that? Very quickly. How would you evaluate this integral? You sub. We're going to put u to be 1 plus 9 over 4x. The du is derivative 9 over 4x is 9 over 4 dx. So this will be equal to, I'm going to change the limit as well. If x is 1, x1, it means the u is 1 plus 9 over 4, 4 plus 9, 13 over 4. If x is 4, then my u is 10. Sorry. This is 10 and this is 13 over 4. Square root of u. Now the dx. I solve for the dx. I get 4 over 9 du. And the rest become a very simple integration. So it's 4 over 9. Integral from 13 over 4 to 10. U to the power a half du. U to the power a half is 1 over a half plus 1. So it's 4 over 9 times 3 half, 2/3. U to the power 3 half. Since I changed my limit, I don't have to worry anymore. 13 over 4 and 10. And then we finish the problem. Yeah, if you want to. If you want to. I don't really care. You can change them at the end. Absolutely, Erin. Okay. Question number 2 is the following. I want you to use what we've learned to find the circumference of half a circle. So question number 2 is, I will give you the picture. That's half a circle. And I'm going to use what we've learned to find. So let us say this is a circle of radius 2. And the question is, use what we've learned to find the circumference or the length of half circle using the of radius 2. All right, how would you do that using what we've learned? Quickly. Okay, so I give you this length and tell you, okay, now we know how to find the arc length of a curve given by a function. How would you find the arc length of this circle? What do you think you need? I'm listening and reading. The formula of a semicircle. Thanks, Aaron. What's the formula of a semicircle? I've talked about it. I would like you to start internalizing it. What's the formula? Ouch. That's not if that's the formula for the value. No. I need the function. No. What is the function whose graph is a semicircle? What is the function whose graph is a semicircle? Right, now we're talking. The equation is x squared plus y squared equal r squared. Okay, so if I want to use what we've learned, I need a formula for the semicircle. How can I find a formula? I did not give it to you on purpose because I want to bring this back up. That's a circle of radius 2. The equation is x squared plus y squared is, let me erase the 4 here and write the radius square. That's the equation. It means x squared plus y squared equal to 4. That's the equation of a circle. Now I want the function whose graph, when you graph it, you get the circle. I want the upper half, so I need to solve for y. Y will be 4 minus x squared, and it's the square root of that. So the function is y equal the square root of 4 minus x squared. Right, so if I want to use what we've learned to find the circumference, remember circumference, not area, the circumference or the length of this picture right here, what I need is the function that gives me the graph. So this would be the graph. So now I can rephrase my question and I tell you, or find the length of the curve given by f of x equal the square root of 4 minus x squared for x between -2 and 2. Okay, so I can either ask you the question and I expect you to be able to find it, which is I do by now, or I can rephrase it in this format. So if I want to use the linked formula, I need to find the derivative. So I need the derivative. Since I need the derivative, I have to rewrite this to the power a half. So what is f prime? F prime is the chain rule. It's a half times 4 minus x squared times the derivative of what's inside. So now if we simplify this little bit, 2 and 2 cancel each other out. I will have minus x over the square root of 4 minus x squared. So now I need the length. The length is the interval from -2 to 2 of the square root of 1 plus this dx. And this is minus x over the square root of that. Okay, so finally this is equal to the integral from -2 to 2 of the square root of 1 plus. Now this is minus squared become positive. I will have x squared here over 4 minus x squared. Oh, ouch, I did a mistake. I don't think you can integrate this. Can you change to 1 to make our life easier? I would like you to change everything to 1 just because we're not ready to integrate that. We can only integrate it with 1. So please change all of it to 1 and then it will be much easier. Okay. Now we're stuck in a way, not stuck. So this is -1 and 1. Everything -1 and 1. Very good. So now I have to integrate this. If you were me, what would you do? Anybody have any idea? Of course, we know that we can never split a square root. We know that we cannot simplify by x squared. So what would be a good approach? Okay, we're going to find a common denominator. 1 minus x squared plus x squared over 1 minus x squared. So this would give me common exactly. Integral from -1 to 1 of minus minus, cancel each other out. And I will have the square root of 1 over 1 minus x squared dx. So finally, it's the integral from -1 to 1 of 1 over that. And now what's the function? Which derivative is 1 over the square root of 1 minus x squared. That's why I have to change to 1 because 4 is, you don't know it. Anybody knows which function has for derivative 1 over the square root of 1 minus x squared? Okay. It's the arc sine x evaluated between -1 and 1. And now we have it. That's arc sine 1 minus arc sine -1. Now, arc sine 1, the angle whose sine is 1 is pi over 2. Minus the angle whose sine is -1 is minus pi over 2, and that will give me equal to pi. It means that if you take this, which is, of course, we know it, that's the arc length, it's not the area. We know that, so our formula give us pi. What they taught us in middle school or high school, the circumference is it's 2 pi r. So this is gonna be pi r. So it's, or if you want, the circumference is a half of 2 pi r, and which is in this case equal to pi, which is exactly what we got. So what we are really looking for is just the length. That's how much this graph here is the length of this graph. Okay. All right, so please make sure to do the homework and start working on the review. I know that the answers are not there. They will be there tonight because all my work is in my office and I need somebody to go to my office and actually email it back to me. But get started. I will ask you a question about differentiation on the exam. So please make sure you do the part about differentiation. You cannot afford forgetting how to differentiate when we are working with something very different at this stage. All right. Any question before I let you go? You're very quiet today. I hope tomorrow you won't be that quiet. Any questions? Okay, have a good rest of the week. Bye-bye, guys.